Okay, in this video, we'll take a look at how to use the first derivative to find intervals where a function is increasing or decreasing. Now, to do that, we'll actually follow this series of steps, but this process will actually make a lot more sense if we look at a graphical example first. So let's go ahead and do that, then we'll come back to these steps. Now, to begin with, let's go ahead and sketch a graph to see how the first derivative ties into all this. Now what I'm going to do is this, assuming that the graph does the following. Let's suppose it starts right here, and it goes up and hits a maximum right there. Then now in this interval it would be increasing, hits a maximum here, and it switches to decreasing. So the function, let's assume it continues to decrease until it gets down, say to about right here. Then it hits a bottom, and it switches back to increasing again. So the function begins to increase, and then let's do this. Let's assume it levels off just for a second here, and then continues to increase again. And then finally, we'll assume it hits another maximum over here and switches back to decreasing. And we'll put some arrows on the end of this thing to indicate that it goes on forever. So that's what the situation looks like. Now, if you have the graph, it makes it very easy to figure out intervals where it's increasing or decreasing. Remember, if it goes up, it's increasing. If it goes down, it's decreasing. Now, we've talked about this before, but we'll go ahead and put critical points on this. Now, what will happen is wherever it hits a maximum right here, it switches from increasing to decreasing, and that occurs, you've got a horizontal tangent right there, which tells you that the first derivative is equal to 0, because the first derivative is the slope of the tangent line. So it goes from increasing, hits a maximum, and switches to decreasing. Then when it gets down here, it hits what's called relative minimum. You have another horizontal tangent, and again, this occurs where the first derivative is equal to 0. Then it switches back to increasing, and let's go to this point right here, and we'll assume that just for a second we have a horizontal tangent right there. So again, the first derivative is equal to 0. And then finally, another point over here hits a maximum here, it goes to increasing. Now in this interval it went from increasing, hit a horizontal tangent, and continued to increase. At this point, it has a horizontal tangent, so again, f prime is equal to 0. So each one of these things is a critical point. Now, what I'm going to do is to draw a line through those. So we'll do the following. We'll draw a vertical line where it divides this thing up into intervals. So we'll start from here and go down to here. Then I'll draw one from here and go down to, say, here. Then I've got another interval that goes from here, and we'll say it goes right through that critical point down to here. And then finally, I've got another one that goes from here, and I'll go straight through the critical point down to, say, here. Now what this does, it actually gives you 4 intervals. So what happens is the first interval goes from here to here, basically from negative infinity to right there. The second interval goes from here to here. Third interval from here to here. And fourth interval from here to here. And actually then I've got a fifth interval that goes out here and goes off to a positive infinity. So what happens is if you're trying to find intervals where the function is increasing or decreasing, it will switch from increasing to decreasing at a critical point. Now it doesn't have to. In other words, look at the example here. It went from increasing to decreasing, it switched at a critical point. It went from decreasing back to increasing here, switched at a critical point. But it's not required to do that. Just because it's increasing, if you hit a critical point, doesn't mean that it has to switch back to decreasing again. So you could have this situation. It went from increasing, hit a critical point, and continued increasing. But the idea is that the critical points will determine the intervals where it might switch from increasing to decreasing. Now, within each interval, you can do the following. If you want to know whether it's increasing or decreasing, this time we'll go ahead and we'll draw a tangent line at each point. So what we're going to do in this process is this. We'll first of all identify the critical points where it might switch. Now, each one of these things, wherever the horizontal tangent is equal to 0, is a critical point. So we'll put a CP right there. So that's a critical point. That's a critical point, and that's a critical point. So the critical points determine where the function might switch from increasing to decreasing. But to figure out what's going on in each interval, here's what you have to do. You have to pick a convenient test point inside each interval. So what I'll do is pick a point. Suppose I pick this point right here. Then I'll evaluate the slope of the tangent line right here. Now in this case, the slope of the tangent line right here is positive. So what that means is f prime is positive. If f prime is positive, the slope of the tangent line is positive, that means in this interval, the function is increasing. Then I'll do the same thing. Pick a convenient test point here, evaluate the function at that test point, find the slope of the tangent line. In this case, f prime would be a negative. So it's positive here, which means it's increasing. It's negative here, which means it is decreasing in this interval. Then again, I'll pick a convenient test point, say right here. Find the slope of the tangent line at that point. That's got a positive slope, which tells me that f prime is positive. It's increasing. So in this interval, I know that it is increasing. Then in this little interval over here, again, I'll pick a test point, find the slope of the tangent line. The slope of that tangent line is positive, which tells me that the function has to be increasing in this interval. And then finally, I'll pick a convenient test point over here, find the slope of the tangent line at that test point. That's negative, which means that f prime is equal to a negative. If the first derivative is negative, that means that this function is decreasing. So that's going to be the strategy that we use. Now, finally, the last thing to notice is this. Whenever you go from increasing to decreasing, and I think I'll put this in black, if you go from increasing to decreasing, then that means you have a relative maximum right there. So right there we had a maximum. If you go from decreasing to increasing, you'll have a relative minimum. So I got a relative minimum right there. Now finally you can have this. If it goes from increasing to increasing, then you would have neither. You had a critical point, but it's neither a maximum or a minimum. And then finally, if you go from increasing to decreasing, in other words, from positive to negative, again, you'll have a maximum just like you had at this point over here. So you've got maximums, minimums, a maximum, and if it doesn't change sign, then it's neither. Okay, so with that in mind, now let's take a look at an example. Okay, now, first of all, we'll go to our rules. Now, we'll follow this series of steps. So the idea is this. We'll find, first of all, we'll need the first derivative to identify the critical points. So find the first derivative. Now, the critical points occur where the first derivative is equal to 0 or is undefined, but in our first example, we'll only look at where it's equal to 0. Once we set the first derivative equal to 0 and solve for x, that'll give us the critical points, and we'll use that to divide the graph up into separate intervals. Then to find out what's going on in each interval, we'll pick a test point, and I want to emphasize convenient test point inside the interval, evaluate the derivative to see if it's positive or negative. If the derivative is positive, then that means that the original function must be increasing in that interval. If the derivative is negative, then the original function has to be decreasing in that interval. Then we'll also look at something called the first derivative test in just a second to show what that goes. But first of all, we want to find out intervals where it's increasing or decreasing. So with this in mind, now let's try an example and see what this looks like. Okay, so here's our first example. We've got a function and we want to identify intervals where it's increasing or decreasing. So let's go back just to review a series of steps and stay with this. Okay, the first step is go ahead and find the first derivative because you're going to need the first derivative to get the critical points. So I'll go back to the function and we'll do this. Step number 1, is to find f prime. So we'll put it right here. Step number 1, find f prime. You want the first derivative. So in this case, the first derivative would be the following. I'll have f prime of x is equal to, now when you find the derivative of this, use the power rule. If I bring the 3 down, this will turn into x squared. The derivative of this would be minus 2x, and the derivative of this would be minus 3. So what this does, this gives me the first derivative. So there's the first derivative. Now, let's go ahead and look at the next step. The next step in the process is you want to find the critical points, and you find the critical points by setting the first derivative equal to 0 and solving for x. So let's do that. So step number 2, take the first derivative and set it equal to 0. So x squared minus 2x minus 3, and set that equal to 0. This is going to identify the critical points. Now this one you can go ahead and factor. So this will factor into an x minus 3 times an x plus 1. And that's going to be equal to 0. Now, to identify where this thing's equal to 0, go ahead and set each factor equal to 0. So set that one equal to 0 and set that one equal to 0. If you solve this one, x minus 3 is equal to 0. That gives you x is equal to 3. If you set this one equal to 0, x plus 1 is equal to 0. So x is equal to a negative 1. Now what this does, this gives you 2 critical points. So this right here would be a critical point, and this right here would be a critical point. Now what these are points where you're going to have a horizontal tangent. And you don't have to do this, but this process will make a lot more sense if you sketch a graph. So we'll go ahead and sketch a graph on this one. So what I've got is something that looks like this. We'll go ahead and put a negative 1 right here. So we have a critical point right here at negative 1. I've also got a critical point at 3, so I'll go ahead and put 3 right over here. And that's also going to be a critical point. Now what that does, that divides this thing up into intervals. So I'll go ahead and, put those intervals on there right now. We'll assume that this first interval goes from here down to right here. And the second one goes from here down to right here. So I've got it divided up now into 3 intervals. So let's go ahead and put this across here. You've got a first interval right here that goes from negative infinity to negative 1. You've got a second interval that goes like this, that goes from negative 1 to 3. And finally, you've got a third interval that goes over here that goes off to a positive infinity. So there's your 3 intervals. Now you got to figure out what's going on in each side of those intervals. Is it increasing or decreasing? So let's go back to our series of steps and see what happens next. Okay, we've already done step 3. Use the critical points to divide the graph up into separate intervals. So now we go to step 4. And the idea is this. Pick a convenient test point inside each interval. Evaluate the derivative to see if it's positive or negative. If it's positive, the function's increasing. Negative, the function's decreasing. So let's go ahead and do that. So this is going to be step 3. And let's see, we'll switch black on that. So it looks like this. Step number 3. Now, when I say a convenient test point, you can pick any number you want to in here. I say convenient because don't pick a fraction if you can avoid it, because it stays away from fractions. But what I'll do is this. I'm going to pick a negative 2. That's my first point. Over here, I'm going to go, might as well pick the easiest thing I can pick. And the easiest thing I can pick here, I'll pick 0. Now, if you wanted to, you can pick a 1 or a 2. It's your choice. And if you wanted to, you can pick a fraction. And over here, I'll pick a convenient test point, and I'll just try to stay with integers. I'll pick a 4 on this one. So those are my test points. Now, what I want to do is to evaluate the derivative at those test points to see if it's positive or negative. If it's positive, it's increasing, negative, decreasing. So I would suggest build up a table, and I like to do them in order from left to right. So what I'll do is this. I'll put the first derivative evaluated at the first test point. Then below that, I'll put the first derivative evaluated at the second test point. then I'll put the first derivative evaluated at the third test point. So again, make sure you pick a point inside each interval. Okay, next thing, go ahead and just take these values and plug them into the derivative. So when I plug it in, this would be negative 2 squared minus 2 times a negative 2 minus 3. And when you evaluate this, it will turn out to be 5. Now, you're not so much concerned with the numerical value of this as much as you are just whether it's positive or negative. I think I'll actually put a positive 5 there to emphasize this. It turns into a positive 5. And what that means is this thing is positive, which means the function is increasing in this interval. So it has to be increasing, and at this point I can go ahead and write the interval notation. It is increasing in the interval from negative infinity up to a negative 1. Now, it's an open interval here because when x is equal to a negative 1, you have a horizontal tangent and it's neither increasing or decreasing. So there's the first part of the answer. It's going to be increasing. If you want to, you can come up and just write increasing right in here. So it has to be increasing in this interval. Now let's figure out what's going on in this interval. Go ahead and plug a 0 into this thing. So 0 squared minus 2 times 0 minus 3. And if you evaluate that, you get 0 minus 3, which would be a negative 3, which is a negative. So in this interval, the value of the first derivative is negative, which means that it is decreasing. So it's going to be decreasing on the interval from negative 1 to 3. So from negative 1 to 3, it has to be decreasing. Now let's find out what's going on in this fourth interval, or third interval. We'll go ahead and plug in a 4. So 4 squared minus 2 times 4 minus 3. And what that's going to give you is a positive 5. But the point is that it's positive. Again, you really don't care if it's a positive 5, a positive 7, a positive 12. It's just a positive. So the number doesn't make any difference, but it is a positive, which says that it is increasing. So now you know it's going to be increasing on the interval from 3 all the way out to a positive infinity. And this is the first answer, part of the answer to your question. So the question was to identify intervals where it's increasing or decreasing, and we can go ahead and put a black box around this. So it looks like this. Here is the actual answer to the question. So identify intervals where it's increasing or decreasing. So it looks like that. Now what we're going to do is look at one more thing here. You can actually sketch a graph of it and see what it has to look like. And we'll also show how the first derivative test ties into all this. So first of all, I'm going to go ahead and just roughly sketch a graph and see what this thing would look like. So it would do this. Now here's the things that I know. I know it's going to go from increasing in this interval to decreasing in this interval, which tells me that it has to hit a maximum here, and I've got a horizontal tangent. So the first thing I'll do is I'll come over and I'll put a horizontal tangent right there. And that horizontal tangent is where f prime is equal to 0. Now the graph has to do this. It has to go from increasing over here, it has to hit a horizontal tangent right there, and then it switches to decreasing over here. So it's got to look roughly something like this. Now, at this critical point, it does the following. I've got another horizontal tangent, but it's got to go from decreasing to increasing. So decreasing in this interval to increasing in this interval. So I know I have to have a horizontal tangent right in here. So again, this is where f prime is equal to 0. So let's go ahead and sketch the graph. The graph must look something like this. It has to come down like this. It has to level off at a horizontal tangent right there. Then it has to switch back to increasing again. And that's what the original function has to look like. Okay, now, even though the problem didn't ask for it, there's something called the first derivative test. And let's take a quick look and see how the first derivative test ties into all this stuff. Okay, now here's what the first derivative test is. It says this: if you have a critical point for a function, then the following is true. If the derivative changes from a positive to a negative at the critical point, then the function has to have a relative maximum there. If it goes from a negative, and well, the way to look at this one, if it goes from increasing to decreasing, you have to hit a relative maximum. If it goes from decreasing to increasing, you have to have a relative minimum. And finally, there's a possibility that it may go from decreasing to decreasing again, so the sign doesn't change. In that case, it would neither be a relative maximum or a relative minimum. So let's keep these two in mind now as we look back at our graph. So what happens is, at the critical point, at the function, and let's look at these two, we'll go to red here. The function went from increasing to decreasing. So it went from increasing to decreasing. Therefore, this must be a relative maximum at the critical point, x is equal to a -1. And if you look at the graph, sure enough, you can see that it went from increasing to decreasing. So sure enough, you have a max right there. Then the other possibility, at the second critical point, it went from decreasing to increasing. So now we'll look at these two. It went from decreasing to increasing, which the second derivative test, or the first derivative test says that if it goes from decreasing to increasing, then you have to have a relative minimum right there. So what that means is it went from decreasing to increasing, therefore you have to have a relative minimum at the critical point, x is equal to 3. So again, that's just to show you where the first derivative test ties into all this. So let's go and we'll take one last look at the first derivative test. Now here's what the rules say, and we'll apply it to our original graph to see what it says. So again, if the first derivative goes from positive to negative, in other words, increasing to decreasing, you have to have a maximum. Now let's look back at our original graph up here, and you'll kind of see on each one of these. It went from increasing to decreasing, sure enough, you have a maximum. If it goes from decreasing to increasing, you have a minimum. Now let's look at that third possibility. The third possibility says this. If the derivative does not change sign at a critical point, then you have neither a relative maximum or a relative minimum. And an example of that would be this thing right here. It goes from increasing to here, hits a critical point, but increases again. So the sign was positive, it stays positive, the sign doesn't change, so you have neither a relative maximum or a relative minimum. So that's the third possibility. So again, that's all the first derivative test says. It's just a quick way of identifying whether you have a relative minimum or a relative maximum. But the steps to finding increasing and decreasing intervals, and we'll go back and take one last look at that. If you follow this series of steps, the critical points divided up into intervals, then again, pick a convenient test point inside each interval to see if it's positive or negative. If it's positive, it's increasing. If it's negative, it's decreasing. And then, although you don't have to do it, I think it helps if you sketch a graph and it'll give you an idea of what's going on. So that's how to use first derivative to find intervals where it's increasing or decreasing, and just a quick look at the first derivative tests.